So in this video, we're going to talk about reactions of HNO2 with primary amines, secondary amines, and aromatic amines. So HNO2, or nitrous acid, I think, can't be formed in solution. So you have to make it with Na, NO2, and HCl, some sort of acid. So when you react a primary amine, HNO2, oh shoot, that's not in the amine at all, H2, form Diazo compound. It's pretty unstable. It's gonna readily leave because it forms nitrogen gas, which is a good leaving group. For a secondary amine, HNO2, you form something like this. We call this a nitrosamine. It's probably toxic. And for tertiary ones, the ones that are attached to three things, HNO2, and oh, cool, but we don't really care about these, so we don't worry about it. So let's talk about the mechanism of formation. Mech with primary. So we know that in solution forms nitrous acid, right? And then further reacts with HCl. So we're gonna have an acid-base step. H2 plus, Cl minus. And here, now that we have a good leaving group, these lone pairs from the oxygen are going to come in and kick the water out. H2O plus O triple bond N. Cool, and that's step one. Now in step two, we're going to have our amine. Here what's going to happen is our amine is nucleophilic and it's going to attack the nitrogen. N, H, N, O. But remember, our goal is to form the triple bond N. So eventually we know that this O has to leave. And the only way that it can leave is that if we transform it into water. That's exactly what we're going to do. We're going to have a series of proton transfers. H, N, O. Here for draw resonance. That nitrogen is actually supporting that oxygen and making it more basic. So, if it's more basic, what's it going to do? Another acid-base reaction with the acid that was just formed. So here we're getting closer and closer to eliminating that O, OH. And here the water was formed again. Another acid-base reaction, and again, there's going to be another acid-base reaction. NOH plus HOH2 plus another acid-base reaction. And H2 plus H2O. And again, in order to get that triple bond, these lone pairs are going to come down and kick the water out. R, N plus H2O. Cool. And that is our product. So, now reactions involving primary diazo compounds. So let's say we have this compound, NH2. So we react with Na, NO2, and NaHCl. You form N2 plus. Remember, it's nitrogen gas, so it's a really good leaving group. It's just going to dip. So you lose this as N2 gas. Now you have a carbocation. If you have heat, then you eliminate. If you have a low temperature, low T, or anything else, you're going to have substitution. Substitution. Because it's a carbocation, be careful of rearrangement. Now, what happens if you use NaNO2, 2SO4, and H2O? Well, the same thing is going to happen. Going to form your diazonium. It's going to dip. Now you have your carbocation. If you heat it up, heat tends to favor elimination. Low temperature again, or you just leave it alone. Substitution. But notice here, it changes depending on our acid. Since we use HCl, we have chlorine. But here, since we have used H2O and H2SO4, we have OH. Alright. Now, formation of secondary ones. Formation secondary. So the secondary ones are pretty straightforward. And H, here I'm going to go straight to the nitrous acid part. Or I mean, attacking the electrophile. Because that formation is pretty much the same, and drawing it again would be redundant. O plus. Here the water comes in. Whoa. Here the water comes in. Exit the proton. And you're done. That's it. Now there's one reaction that Nasiri really wants you to be familiar with. Formation of diazomethane. Formation of diazomethane. So here, 2N HO. If you use HNO2, again HCl, again, this nitrogen is more basic because of that methyl group pushing by induction. And if it's more basic, it's going to react. So, and we form our nitrosamine. And if we use a base, KOH, H2O, we form diazomethane. This compound turns into this. Now, reactions of diazomethane. If you have a carboxylic acid, CH2 and 2, you create a methyl ester. And then if you have an alkene, you create a cyclopropane. So enantiomer. Cool. Now, arene diazonium reactions. So we have N2 plus, right? If we have H2O in heat, we can make a phenyl. That's just going to dip and the water is just going to substitute in. If we have H3PO2 in heat, simply NH. CuCN, heat, cyanide group. Notice how this adds a carbon plus COO derivative. So you can do a lot of things with that. NABF4, add a fluorine. Finally, or not finally, CuX, X is Cl, Br and I, heat, X, and then diazonium coupling. Benzenes just coupled together. Now briefly, I'm going to talk about diazonium coupling. Zonium coupling. So remember, the azo compound is getting attacked, right? So if it's getting attacked, it's an electrophile. So for a good electrophile, we want this to be electron poor. So we want it to be deactivated. Hence the nitro group. And if it's deactivated, there's a bigger positive charge. And then our compound that is going to attack want to be electron rich, activated. We want to be electron rich to give it more electron density. So when these two charges combined, you will get a more favorable reaction. And can't really draw benzene right now. Pretend that's a benzene, OH, and then NO2. And that's it for today's video. If you have any questions, don't be afraid to ask.